Welcome to the section on document clustering or grouping of documents. In this section, we'll separate the training data into different groups where each group has documents that are more related to each other as compared to the documents belonging to different clusters. The objective of clustering is to achieve high intra-cluster similarity, that is, the documents belonging to the same cluster must be very much alike while achieve low inter-cluster similarity, and that is, the documents belonging to different clusters must be very different from each other. So based on this criteria, the documents are being arranged into multiple clusters. It's an unsupervised learning where the labels are not available and it's not known what each group represents. In other fields of study, it's also called sorting or segmentation. There are two main types of clustering. They are called the partitional approaches and the hierarchical approaches. In case of partitional approaches of clustering, the data is being separated into the desired number of clusters all at the same level. For example, if we have a dataset of 5 documents and we want to separate these documents into 3 clusters, the distances between all the documents would be evaluated, and finally the algorithm would suggest this separation of documents into the clusters. If we see over here, the documents D4 and D5 has the least distance of 1. Therefore, they are the closest to each other. The next closest are documents 2 and 3 that have the distance of 2. This matrix represents the distances between two documents. So the distance between D1 and D2 is 8. All the documents have distances of 0 from themselves, and the lower part of the matrix is left empty because there is going to be duplicate of the data that we have in the upper part. So partitional clustering would evaluate all the distances, and then based on that will partition the documents into the desired number of clusters all in a single step. In comparison to that, if we consider hierarchical clustering, for the same data set, there are two different approaches in hierarchical clustering that can be followed. In case of bottom-up clustering, that is also called agglomerative clustering. Each document is considered to be a cluster of its own. So since there are 5 documents, we have 5 clusters, each has a single document. In the next step, we are going to calculate the distances between all the clusters, and the 2 clusters that are the closest to each other are going to be merged. So D4 and D5 are being merged. Similarly, in the next step, D2 and D3 are being merged, and since it fulfills the criteria, that is, we wanted to have 3 target clusters, so after this we are not going to merge the clusters anymore, and this is our desired clusters. In case of top-down or divisive clustering, all the documents are being considered to be belonging to the same cluster. In the next step, we are going to separate this cluster into 2 clusters based on the distances, and therefore D1 is separated into 1 cluster while the second cluster has the documents from D2 to D5. And in the next step, we further want to separate our dataset into more clusters. So since D1 cannot be separated any further, this cluster is being separated based on the distances that we have in the table. The documents D2 and D3 is separated into 1 cluster while D4 and D5 is separated into another cluster. And since we have achieved our desired number of 3 clusters, therefore the data is not going to be separated any further. In case of hierarchical clustering, we have seen that at times we have to calculate the distance between a cluster and a cluster, or a cluster and an object. For example, in this case, we are calculating the distance between a cluster that has more than 2 documents and another cluster that has got 1 document. Or in this case, we have to calculate the distance between the cluster that has D2, D3 and another cluster that has the documents D4 and D5. So what we are going to do in case we have to find the distance between 2 clusters or a cluster and an object. There are 4 different possibilities for it. In case of using single linkage, we are going to consider the 2 closest documents belonging to different clusters as the distance between the 2 clusters. For example, among all these 4 documents, the closest documents belonging to different clusters are D3 and D4, and they have a distance of 3. So this is the closest, and this is going to be considered as the distance between these 2 clusters. Similarly, in case of complete distance, the distance between the farthest objects of the 2 clusters is considered to be the distance between the 2 clusters. So in this case, the document D2 and the document D7, the document D2 and the document D4 or D5 has the distance of 7. So the distance between these 2 clusters according to complete linkage is going to be 7. In case of average linkage, the distance between all the documents of the different clusters is calculated and is averaged. For example, we will have to calculate the distance between D2 and D4, D2 and D5, similarly D3 and D4, D3 and D5, add it all up and divide it by 4. The most commonly used approach is the Ward's linkage that compare the two clusters, which achieves minimum variance. That is, we have low dispersion in the data when the two clusters are being merged. So these are the basic types of approaches in clustering. In this lecture, we are going to walk through the algorithm of one of the frequently used partitional clustering algorithm, that is k-means clustering. The first step is to provide the value of k, which represents the number of clusters. So this has to be provided by the user. The user must know the desired number of clusters and has to provide this to the algorithm. The algorithm will then separate out the data into these clusters. Initially, the model is going to throw k different centroids or cluster centers into the problem space, and then finds the membership of each of the instances with these cluster centers. The object that has the closest distance with one of the three cluster centers is assigned to it. So we have all the instances assigned to one of the three clusters. In the next step, the cluster centers are re-estimated and are positioned into the center of the clusters of objects that are assigned to it. Similarly, the process is being repeated where in the next step all the objects reassess their memberships and may switch to a different cluster. In response to that, the cluster centers gets re-estimated. So this process keeps on repeating unless the documents do not switch their clusters and the centroids gets stable. In order to represent this problem visually, the brown diamonds represent our input data and the gray circles represent the three centroids. Please remember that the number of 3 was suggested by the user, while the position of these centroids is picked at random by the algorithm. In the next step, the model has identified the distances of all these objects with all the centroids, and these are the objects that has the closest distance with this centroid, so therefore they are assigned to this cluster. The instances in red have the closest distance to this centroid and they are assigned to this cluster. And then we have the third cluster at the bottom right corner. As we can see, the cluster centers are not positioned into the center of the cluster, so therefore in the next step we are going to find the average of all the instances that are assigned to this cluster and position this cluster center into its average position. So after readjusting these cluster centers, now the objects are going to have different distances from the centroids, and therefore we will have to recalculate them. So in this step, the centroids are being positioned to the center of their respective clusters, and in response to that we can see that objects that were on the edge, now with the center moving away from them, have changed their memberships. Similarly, the clusters are being readjusted while the objects also keeps on changing their membership. Majority of the objects do not change their membership, however the ones at the edges are going to do so. So this is the final representation where centroid of the three clusters is not moved anymore. The objects do not update their membership. So finally this is the clusters that we have achieved. The cluster representing the red diamonds, the cluster representing the brown diamonds, and the cluster representing the green diamonds. In this lecture we are going to implement the partitional clustering algorithms. So let's just get to the code. I'll be using Jupyter Notebook. We'll start a new document of type Python 3. So as always, the first thing that we are going to need is to have a dataset that we can partition. So I'll load the dataset and structure it from what we covered in the last lectures, and we'll be back. Okay, so now we have got some code, and this is from the previous sections. We are reading the data from the dataset, and since our dataset is labeled, we'll be using this labeled dataset for the sake of demonstrations. However, since we will be applying clustering on it, so therefore we will strip off the labels and we'll throw them away because we are not going to need them. So this is what we are doing over here. We are separating the document onto the input part and the label part, and then we are only keeping the input documents. Next, we are importing the count vectorizer, and we are structuring our input data into the form of a matrix. From here we are going to start clustering our input data. In case we are applying k-means clustering, so we'll have to apply k-means from the cluster package of the sklearn library. So from sklearn.cluster import k-means. We'll create an object of type k-means, and out of the different parameters that we can pass to the k-means cluster, then the most important one is to decide what are the number of clusters that we are interested in. So n_cluster is 2. We want our dataset to be separated into 2 clusters. Next, we are going to train the model. So k-means.fit the structured data. So the model is being trained, and now in case we want to see how our dataset is being partitioned into 2 clusters, so we will use the attribute k-means.labels_, and it says that the first 3 documents belong to one cluster it has given it a hypothetical label of 1, while the document from 4 to 6 represents another cluster and is given a label of 0. The labels in clustering do not make any sense. They are just used to represent that this is one cluster and this is another. Therefore, these are not the genuine labels that we would consider to be meaningful. So our dataset is being clustered into 2 clusters. In case we want to train our model on some part of the input and then suggest what would be the cluster of any other document. In case we want to cluster only some of the data, that is the first 5 documents starting from ID 0 to 4. So now we are clustering the first 4 documents, and if you want to see their labels, the first 3 documents belong to one cluster. Now as we can see, the labels are being switched, so the labels do not mean anything other than suggesting that this is one cluster and this is another cluster. If you want to predict the label for the unseen document that the model has not seen, so let's see to which cluster it's going to place it. So k-means dot predict the cluster for the unseen document that is at index 5, and it says 1. So as we saw, we kept one of the documents belonging to the cluster 1, and now when we provided it as a test case, the model says it belongs to cluster 1. So that's how clustering is being performed. Some of the other parameters that we can provide for through the k-means clustering is the maximum number of iterations that we would want the model to settle in. The default value is 300. We can change this value. By giving the maximum number of iterations, we assume that whatever the accuracy is being achieved with these many iterations is going to be good enough. We can also provide tolerance. That means that if too many documents are not switching across the clusters, then this is good enough and we are happy with it. Similarly, we can also provide tolerance is equal to, so if tolerance is less than this margin, we are happy with it and we are not going to achieve any further accuracy. So with the help of tolerance, we can see what level of accuracy is being demanded, and obviously is going to help towards the efficiency. Another parameter that we can use is the algorithm, and the 2 possible algorithms for k-means clustering are full or Elkin. And using any of the algorithm, the k-means, the way this model is being implemented is going to be performed. So this was all about k-means clustering. In case we want to apply the nearest neighbors clustering approach on the same data, so we'll have to import from the sklearn package, from the sklearn library, neighbors package, import nearest neighbors, and we'll create an object of type it, and let's say we call it the nearest neighbors, or just kn. Our object is being created. Next, we can train the model and provide it the structured matrix, that is matrix underscore x. With the model being trained with the default settings, now we can say that if in case we want to see the neighbors for a particular object, we can see using the object kn. So we have given it an object at random, and we are saying that we are interested in the nearest neighbors of this object, that is the objects that belongs to the same cluster and are very close to this object, and we are interested in 2 of the nearest neighbors. So if we execute this, it says the object 3 and 5 are the closest to this object. The object 3 and the object 5 are the closest to this object. So obviously it's the closest to itself, and the next closest is the object 5. With itself it has got a distance of 0, and with object 5 it has got a distance of 1.4. We can also look for the nearest neighbors of any object within the same cluster by providing a certain radius value also. So kn dot radius underscore neighbors. So in this case, we are asking for the nearest neighbors of this object. We are not specifying the number of neighbors that we are interested in. However, we have given it a radius, and we are saying that all the nearest neighbors that fall within this radius value. As we can see, the only object that fall within this radius value is the object itself, with which it has got a distance of 0. Let's say if we give it a slightly higher value, and now it has got 2 objects closest to it. There are object 3 and 5. 3 obviously itself with distance 0, and 5 the object that has got a distance of 1.4. So that's how clustering, partitional clustering, is being applied to divide the data into different clusters. In this lecture, we are going to implement a hierarchical clustering approach, that is agglomerative clustering. So let's just get into the code. We'll start a new document of type Python 3. We'll name it as agglomerative clustering. Okay, so the first thing we need to have is to have a corpus. I'll just quickly get our code from the earlier sections and we'll be back. Okay, so up till this point we are reading the data from the dataset and separating it into different documents. Next we are separating the input documents and throwing away the labels as we are performing clustering. We could have used a dataset without labels, but that is fine. And then we are importing the count vectorizer, creating an object of it, and using its function fit_transform to structure our input data and store it in the matrix_x. So next we are going to import the agglomerative clustering class from the cluster package in the sklearn library. So let's just do that. From sklearn.cluster import agglomerative clustering. Next we are going to create an object of type agglomerative clustering. So let's say we call it ag cluster, and that is going to be of type agglomerative clustering. We haven't played with the parameters so far, so let's just try with the default settings and train our model. So agglomerative class.fit matrix_x, we have provided everything to train the model. An important thing to consider here is that unlike other classification and clustering techniques that we covered, these clustering techniques require the data to be in the form of dense array, and therefore instead of just passing the structured matrix, we have to call the toArray function on it and then pass it on to the fit function for training the model. So now our model is being trained, and in case we want to check the labels, so agglomerative clustering dot labels, and this is going to say that the first 3 documents belongs to one class and the next 3 belongs to another class. So it has identified automatically that the data is of 2 types. We did not provide any labels. The model itself identified that there is a clear separation of 2 types of documents and therefore two different clusters. In the last lecture we used agglomerative clustering with default settings, so this time we are going to play around with different parameters that can be used with agglomerative clustering. So let's just get into the code. This is our code from the last part, and we are using agglomerative clustering with default settings. So by default the model is using Euclidean distance and the full tree is being computed as auto. The connectivity is none, the distance threshold is none, and it's using word linkage. And if you remember from the theoretical difference, word linkage is the distance between an object and a cluster or 2 clusters that is based on minimizing the variance. So that is being used by default. The number of clusters is 2. So this is how the model works with the default settings. Now provide different parameters. So the first thing we are going to do is to provide different number of clusters. And as we can see, although our data naturally belong to 2 clusters, we have forcefully separated our data into 3 clusters. We can see that the cluster 0 is not being broken while the cluster 1 is broken into 2, and now there is another cluster with label 2. It means that this cluster has stronger correlation as compared to this one, and now we have a total of 3 clusters, with the first 3 documents belonging to one cluster, the 4th and 6th belonging to the second, and a 3rd cluster with document 5. Another parameter that we can define with agglomerative clustering is the linkage. We saw the linkage parameter is being used as default, so that we can use our single linkage, or we can also use complete linkage or average linkage. And as we can see now, we are trying to separate our data into 3 clusters using single linkage. We can similarly provide the other values that we can use are complete linkage and average linkage. Let's say we keep it as complete linkage and we want to change affinity, that is the distance measured between 2 types of documents. By default it's Euclidean, so as we said in the theoretical part that we want to keep it cosine because that is more helpful. However, cosine does not work with the word linkage. So in case the type of linkage is word, then by default the affinity has to be Euclidean and it does not accept any other value. So since we have changed it from the default of word to complete linkage, now we can try a different value for affinity and we can provide cosine similarity to it. So the model is being trained and it has predicted the labels as we said. We want our dataset to be in 3 labels. So that was the parameter settings with agglomerative clustering. In this short video, we are going to quickly apply the clustering techniques on a dataset from the UCI repository. So from the UCI repository, we go to the Echo Hotel dataset that has got data as text, and It's plain text that can be used for clustering, and there are a total of 401 instances. So let's just download that. So I have stored the dataset locally and have opened it in my Python code over here. The data is being read from the dataset and is provided into the corpus variable, and then we separate it on next line because each line represents a separate document or review on the hotel, and then we apply count vectorizer on it, transform our data into a structured format. Next we are going to apply the k-means clusters on it. So from sklearn.cluster import k-means, and k-means is equal to k-means n underscore clusters. Let's say we need 5 clusters, and k-means dot fit the structured input data, and these are the 5 clusters that we have got. It's a list that consists of all the reviews, I think 401 in total, and we are given the cluster of each document. So the first few belongs to the cluster 1, then there is one that belongs to the cluster 3, and similarly we have all the instances distributed among these clusters. In case our model on some part of the data and then provide some more instances to see how they fit into the already created cluster. So let's say we provide the first 300 instances as training, and next we want our model, and next we want to see how the model is going to predict labels for the unseen documents. So means dot predict matrix underscore x and predict labels for all the instances from 300 onwards, and these are the predicted clusters for the last 101 instances. In case we want to apply agglomerative clustering, so we'll have to import agglomerative clustering, and next we'll have to create an object of type agglomerative clustering. So our agglomerative cluster is being trained with 5 clusters as we are proposing to get, and we are using word linkage, which was also default, and Euclidean, an affinity or distance based measure as Euclidean, which again was the default choice. So if we train our model, this is how the documents are being clustered. If we change the linkage to single, and instead of Euclidean distance, if we try Manhattan distance, the model is again being trained. However, if we try cosine similarity with single linkage, there is some error, and there says there are some infinite values that is preventing the model from being trained. So probably not all linkages and affinity distances are going to work. One has to look into the dataset and try different values, what works well for a particular dataset. The predict function is not defined for agglomerative clustering, so we cannot add new instances into the already clustered instances.